shirt on. How about those White Sox? 4 or 5 wins in a row. Nice. I went to the game Friday. It was great. Okay, but anyway, nobody cares. All right. So I guess I forgot to put this up at the top. We are on the right thing here. Correct. Good. Right. Yeah, sorry. Okay. So today, just moving on into the notes, hopefully it hasn't been too bad with probability. And I think I've mentioned this before when we talked about cards and dice, things having something in common. Things the word overlap is going to be a big word going on here. So first things first, though, we got to do some symbols. So you're going to see this in a formula here. Nice. Did anyone see that? Right and then disappear. Pen and computer got a new thing going. This is great. Fantastic. I know invisible ink. Nice. I like it. All right. Let's see if we can try. Oh boy, this is going to be great. Let me hit escape or something. Now it appears. You were right. It was invisible. Then it just appeared. Sweet. Okay. Let's try this one more time. Yay. Thanks, computer. AUB, which right off the bat, I am going to call that is a union. What do you do with a union? Union is like a marriage. You bring two people together. So that's what union means. What you should put down is also this means the word or. So yeah, you do add, but then when I talk about intersection on the next part, which sorry for jumping ahead, but that's what's going to happen. That is like and, but it's not in the sense of multiplying. It's that there's an overlap. Something is in this list and also that list. It's double timing these two lists. So union is or, and this means that all outcomes are in one event. Whoa, where'd I lose my E there? We'll call that event A with that little situation up there. The other event B or both. And that's the problem. And we'll talk about that if they're in both what we need to do. So, but really what they are is this is said, well, we'll just leave it at that. We'll talk about mutually exclusive and not mutually exclusive. So, what is this? This is a intersect B. And actually, I might write this like this. This is actually said to be, oh my goodness, that's not the computer. That's my brain zapping. That is an intersection. This is specifically and this means you're in both A and B. So these are outcomes that are in both events. So get rid of the word, get rid of or and add and multiply for a second. This is specific to mutually exclusive. There I go again with my words. And I hope you know what a Venn diagram is. We assume that you know that. Okay, and that is this picture. Like in a Venn diagram, that is some these are these four dots that are in both A and B. All right. We can talk about that when we get to specifics. I'm not going to come up with generalizations or some examples of it until we get to examples. Okay, so then let's get down with the word mutually exclusive, which seems like a complicated scenario. These are events that have no outcomes in common. And again, wait till we get to a example that we're going to go with on the bottom to know what that actually means. Okay, fine. I did say forget about or and multiply or add, but in this case we are. We know that when we are looking for the probability, and I'll give you a mutually exclusive event right now, I guess, and it's going to probably accidentally going to come up here, but what's the probability you roll on a six-sided die a 1 or a 6? Does a 1 and a 6 have anything in common, or are they two completely different numbers on the dice? Two completely different numbers. So we know exactly what we do with that. We find the probability of rolling a 1, which is 1/6, and you add that to the probability of rolling a 6, which is also 1/6. What's the probability of rolling one or the other? 2/6. You have a 1/3 chance of that happening. There is no overlap in those two events. They are mutually exclusive. They are completely different than each other. So exercise that term, what mutually exclusive means and looks like. All right, I have no idea what just happened. Now we just have a blackout. This is great. What do you call this? The opposite of invisible. Okay, great. This is a new one. Oh, whoo. Am I seeing this, or are we all seeing this, or am I just freaking out, man? I just want to make sure we're all in this together. Hey, I've heard that before in the last year and a half. Anyway, you are drawing one card out of a standard deck. Remember, that's what the word or means too. I'm rolling a 1 or a 6. You're only rolling once. You just want to know the probability to get one or the other. Same thing happening here. You're drawing one card out of a standard deck. Find a probability to draw a face card or a red 2 or a 7. So first of all, let's write that down. Let's write that down in terms of this is ridiculous. Now it's reopening. Oh my gosh. I love it. I love it. I love it. I love it. Okay, obviously I'm gonna have to restart my computer after these notes. Something honky is going on here, wonky or whatever, something crazy. All right, thank you. Probably I'm saying thank you to my computer to let me actually do this. Now, the word or is union. Okay, so probability of face card, or let's just say R2, R2D2, nice. And then or a 7. First of all, what's a face card? No time for this. Go flip it over, and you were supposed to put this on your cards. Go ahead. Cards guy over here. I'm worried about him. No gambling when you grow up. Okay? All the suits. Any red 2s or 7s face cards? No. Is a 2 a 7? A 7 a 2? No, they're all mutually exclusive. They're all different. So therefore, I could just find the probability of getting a face card, add that to the probability of getting a red 2, and add that to the probability of getting a 7. And then in this one card, that is the probability of getting this or this or this. So it's something we've already done. All right. Then we'll get to the next one. By the way, how many face cards are there? And I got to get, if you get this wrong, you can have your sheet out in front of you. But if you get this wrong, I can't help you. There's 3 of each suit: Jack, Queen, and King. I always run into this, people that don't know cards. How many red 2s? 2. How many 7s? Really would like to go further into cards and probability, like playing poker. Not that we're teaching, how to gamble. You can play poker for fun. But then probability of getting certain hands with 5 cards and all this other stuff. It's kind of cool. But 6, 18, we're not. Used to get real crazy. I remember teaching cat way back in early 2000s, and we had a whole section on just playing 5-card poker and all the different possibilities of doing these things. Again, not teaching gambling, just talking about probabilities. Cards and dice are always fun with probability. All right, one standard die, probability of rolling less than 3 or greater than 5. Okay, let's write this down. Probability number less than 3. Get this done pretty efficiently so you can walk out of here with barely anything. And hope you feel pretty good about the test. On Friday, less than 3 or a number greater than 5. Is there any overlap here, or are these completely unique? I mean, let's get over that real quick. So there is no overlap. You'll see it on the next page. What kind of questions could be overlap? And then we'll be able to just do this. So just understand what the term mutually exclusive means. All right, careful on less than 3. That's not including 3. So 2 and 1. There is no 0 on a die. So 2 out of 6, and then greater than 5, there's only one number that's greater than 5. Mutually exclusive. Now, when I showed a key on there, when I look at your homework, I hope there's not just answers. That I just don't like that. I feel like that's just somebody that is putting the least amount of effort in, but also maybe copying answers. So, hey, just give me your answers. I'll just write these down real quick and then say homework done. Genius. All right, but I'm gonna at least hopefully have the original fraction down, and then at this point, if you go to the calculator and just type it and get a decimal or a percent, fine. But I'd like to see the original, the emulation of the question, like with all the parts put in there. All right, so just take note to self on that. Just talking about what I saw last hour, a couple of people just putting answers in. All right, non mutually exclusive situations, they have something in common. I like the word overlap. And if you don't account for it, you're actually I'm going to use the word double counting, but it could be even more than that if it overlaps in a situation. But you're double counting an occurrence. I love saying that, and it probably won't make sense until we'll actually see this. Unless you use the formula correctly. So if you don't think about the overlapping event, you're double counting a card. You're double counting like an occurrence on the dice, and you got to account for that and take care of it. So here's the formula. So you are unioning two events. What's the probability of this or that? So it does start off. Sure, you add those. But then what you have to do is take the probability of both occurring, meaning the overlap. I overdid a parenthesis there. You got to subtract out the repetitiveness of the scenario. Because here's what's going on in a non mutually exclusive event. I lost my draw there. An event is in this list and in that list when it only occurs once. You're double counting it, and we'll see that in an actual scenario. So what you got to do is subtract out that repetitiveness. That's what that last part is. That's why I added that in the notes compared to last hour. And you don't really need those words. You'll make sense out of it right now. Right now. You're drawing one card out of a standard deck. They shouldn't. Yeah, I guess that's good that they tell you that. But remember, ors, you're only ending up with one card in your hand. Find the probability of drawing a heart or a face card. What instantly is problematic with that? The heart face cards. So here's where, if you were just not thinking about this, probability of here come my drawing skills. Heart, union that with a face card. I should put a face there, like a picture of a king. But no, that could just mean kings then. So I just had to have a face card. If you weren't even thinking, then you would do this. So that heart didn't work out so well. Plus probability of face card. How many hearts are there, by the way? We need to know this from our cheat sheet. There's 13. And then how many face cards are there? Well, we got to think about that. There's 3 each suit, and there's 4 suits, so there's 12. The probability or the problem is who's in this list twice? 3 of them, the king, queen, and jack of hearts. So the king, queen, jack of hearts is in this list, and in this list, there's only one of such card, not 2. So therefore, you must subtract out the heart face cards. So that's what this means. How many of them fall in both categories? All right. So therefore, we subtract out, there's 3 heart face cards. So that makes non mutually exclusive very simple. I know you can think of it in general. You can think about how many hearts are there, how many face cards. Oh, let me get rid of the heart face cards, though, then add them, and you'd end up with the same answer. But this is much easier. Just do this, do that, and then subtract out the repeats. All right. So that's 25, 24, 23, 22. And then 2 goes into both of these. So again, you button pushers or maybe bums that are copying answers, I need to see that first, and then you can do what you want. All right. And we better get there on our homework. So yeah, just saying. Okay, to standard die, what is probability rolled is less than 4 or even. Okay. So probability of a number less than 4, union that with even. I'll just put Eve. Eva. Anyone know that movie? Nice. At least you know that one. I feel like sometimes they do these references and you guys don't know, like, ba la 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 la. What's that movie? Big Hero 6. Good. I mean, you're my oldest daughter's age. You guys should we watch those movies without it. We never missed one of them. Probability of even, and then subtract any number that's in both of these lists. Sorry, less than. Intersect with even, and understand what that intersection thing means. Okay, less than 4 is 3, 2, and 1. So that's a 3 out of 6. Even is 2, 4, 6. How many are both even and less than 4? 1, right? The number 2, but it's one of them. Correct? Right. And I know you can figure this out and and just kind of do it, but just go with the formula because of our next example. That's reduced. You want to make it a decimal or percent, you go for it, 5/6. Now, this is where we get these questions, which are kind of weird. And again, these are just those annoying math questions. They're just done so you exercise a formula, and it's true. But of the students surveyed, 92 either own a car or a computer, but they could own both. That's what the problem is with an or question. This or that, but you could have both, and we don't really know. So there's 92 out of 100 that at least own one or the other. Also, 65 own cars, 82 own computers. Looking at these two numbers, the fact when you add these two up and it's larger than this, that means we have some overlap. And I hope you understand that as we move forward. So 65 just own a car, 82 just own a computer, but there is a certain amount that own both, and it doesn't reflect in these first two statements. So, what is the probability that a randomly selected person owns both? That's where we go into our standard formula here. I guess I'll put car, the whole word. Union that with computer. That equals the probability that you own a car plus the probability that you own a computer. And then minus if you own both. And this formula will tell you how many that is. It's actually an easy way that you can figure this out as you see what happens here. But one or the other, there's 92 out of 100. Probability that you own a car if I picked you, and only a car. Probability that you own a computer, don't know why I did that. 82 own a computer. What's the probability that you own both? That's what I don't know. Yay. That actually works now. Slamming the back of the pen actually gets my pen back. Really, what you can think of this is this is x. I didn't just cross that off, but this is a grade school equation. I'm solving for that last variable. And that's what you can think of this as. Solving for that unknown. So I did not x that out. I'm just saying, let's solve for x. First thing I would do is add those two fractions, 147, I believe. Then you'll ultimately see how this goes about. I'm going to put CA. I'm going to shorten this down to CO. And then the next step is subtracting. And of course, when you subtract 147 from both sides, 92 minus 47 is 47 plus 8, negative 55. over 100, but that equals negative probability of CA intersect CO, and then we're going to turn those into a positive by dividing. So 55 own both. It really is the subtraction of 92 minus, or 82 plus 65 minus 92 ultimately, right? And that's how it happens pretty fast. So of the 65 that own cars, 55 of them own both. Of the 82 that own computers, 55 of them own both. And that's how they're in the double list there. That's how they're double counted, is what this means. And then this is really just more of the same, and I feel silly doing it, but it really is. Survey 90 of them like orange juice or lemonade. Great. 62 like orange juice, 43 like lemonade. What's the probability that they like both? So 90 over 125 equals 62 over 125 plus 43 over 125 minus, we could put x, the probability though of liking both orange and lemonade. I think last hour I just did O and L. Okay, so it's really the same thing. I'd write, probability of this or that, orange or lemonade, equals probability of lemonade plus probability of orange. I switch those two, it's fine. Then ultimately what you end up doing is taking 62 plus 43 and subtracting it from 90. So I think you could do this pretty quick. That's 105 minus 90. When I get this, you ultimately are subtracting 105 minus 90. Squeeze a 2 in there. Okay, so same thing. When I subtract 105, I get a negative 15, but that's a negative probability. Divide by a negative and it turns positive. 15 over 125 is actually 5 goes into 15 3 times. 5 goes into 125 3/25. But really, what ultimately 15 of those in the survey like both kind of thing. So that's how you use your non mutually exclusive formula for these last two cryptic word problems. All right. Would have known how to do that before this. After seems pretty simple. I guess I could. I was going to reach for my mouse, but I can't find it. So I got to go to this. Stop sharing.